Now, next session will start by Dr. B. Nagendra Babu sir. It's our honor to introduce our resource person, Dr. B. Nagendra, an industrial postdoctoral research fellow, Prysmian Group R&D Center, Milan University of Salerno, Italy, under the supervision of Dr. Ferrugi Lydia and Professor Gaetano Vera. Sir pursued his master's in organic chemistry from the University of SK University, and later on he completed his PhD in chemistry on Academy of Scientific and Innovative Research at NIIST Trivandrum. He is a pioneer researcher in several areas like morphology of semi-crystalline polymers, retardant polymer materials, hybrid polymers, and low-dimensional filter nanocomposites. He has pursued and publications 45 research articles in international journals. Sir is a recipient of many prestigious awards and honors like Best Poster Award at Material Science Society of India held at Jorhat, Assam. Best Poster Awards at NIIST, Trivandrum, and Kerala University. He has achieved many patents on different concepts and is still continuing to cable applications and formulations. Sir has attended several conferences and presentations at national and international level on advanced materials, polymer, solvent complexes, and intercalates, and many more such conferences. We are highly privileged to have an eminent personality who will be sharing valuable insights with us. We welcome you, sir, and request you to take over the session. Thank you, sir.
Okay, madam. Thank you so much, madam, for your generous introduction, and thank you so much for your initiative for the inviting me, given my valuable research activities. First of all, am I audible, madam?
Yes, sir, you are audible, sir.
Okay, thank you. Let me share my screen. Okay, can you see the slides, madam?
Yes, sir, they are visible, sir.
Okay, thank you, madam. Thank you for the gates for giving the opportunity. Today I'm going to talk to you about the functional nanoporous crystalline polymer from fundamental to their application. Okay, before going to the discussion about the functional nanoporous film, let us discuss about the polymer, their importance in our daily life, and their importance in the various material applications. You know, the polymers are very important material. We are daily using the many of the applications. For example, you can see polymers in the home, hospital, in offices, all around us. So polymers are a very important material. So why we are choosing the polymer instead of the traditional materials like metal, ceramics, glass, wood material? Because these polymer materials have some extraordinary physical properties, such as they are very lightweight and flexible. So therefore, very easy to use this one and easy to reprocessable these polymers. So we can produce a bulk amount of the polymer in the industry level. And these polymers are easy to recyclable, and also they are chemically stable and electrically insulating. These are also other important properties. They are very safer to use the material. And final but not least, that is cost effective. So these are very cheaper material. So because of combination of all these extra physical properties and cost effectiveness, always we prefer in the polymer material instead of the traditional material. So some of these are advantages of the plastic material. Now we understood the importance of the polymer, their role in our daily activities. So let us learn about the polymer chemistry in the coming slides. First, polymer or macromolecule, nothing but it's a large long chain molecules are called polymer. These polymer molecules are made up with the small molecule. Those are called monomers. Here, the polymer can be classified into two categories depending on the monomer involved in the polymer formation. Those are homopolymer and copolymer. Here the homopolymer, first the homopolymer nothing but the polymer backbone made up with the only one kind of monomer, that is called homopolymer. Example you can take for this one, polyethylene. polyethylene. Here polyethylene is made up with the only one type of monomer, that is a pure ethylene molecule. So that's the reason, therefore, it comes into the homopolymer category of the polymer, this one. The second polymer, that is a copolymer. Here the polymer backbone, it is made up with the more than one kind of monomer. Those are called copolymer. We can take the example for this one, styrene, butadiene, rubber. Here the styrene is a different monomer, butadiene is the other different monomer. Here the polymer is made up with the two different kind of monomer. So therefore, this polymer is a kind of a copolymer. Here, the subject of the copolymer science, it's very complex. We are not going to discuss about the copolymer. Mainly, we are talking about the homopolymer is our topic of the discussion. Coming to the polymer architecture, it speaks about the polymer backbone architecture. So depending on the polymer chain architecture, polymers has been classified into three categories. One is the first one, thermoplastic polymer. This polymer has a very simple linear chain polymer. Those are called thermoplastic polymer. Example for the thermoplastic polymer, you can take a PET, polypropylene, polystyrene. These are the classic example for the thermoplastic polymer. And the second one is the elastomer. Elastomer is nothing but the partially cross-linked polymers are called elastomer polymer. These polymer, you can say the red spot indicated for the cross-linking units, this one. Because of this presence of the partial cross-linking, this polymer acting as a elastomer in the nature. Example for the elastomers, you can see polybutadiene is a classic example for this polymer system. And third in this list, thermoset polymer. It's a highly cross-linked, three-dimensional cross-linked polymers are called as a thermoset polymer. Example for the typical thermoset polymer, polyepoxy resin, polyurethane. These are the classic example for the thermoset polymer. Here, these are the three names like a thermoplastic, elastomer, thermoset are commonly used in the polymer chemistry for the class with the polymer. Okay, coming to these particular system, the second thermoset and elastomer, they have the cross-linking in nature. Because of the presence of the cross-linking nature, these polymers are not easy to melt and reprocessable. Due to that, these polymers are not a sustainable recyclable polymer. Whereas in the thermoplastic polymer, it's a simple linear chain polymer, very easy to recycle. So these polymers are considered the sustainable polymer. So we are also interested in the sustainable polymer, our activity. So next, coming to the polymer structure and property of the thermoplastic polymer, the structure plays a very important role in the design, the macroscopic property of the polymer. For example, you can take a polymer chain. This polymer chain made up with the two different monomer. For example, one example, you can take a polystyrene. Other one, you can take a polypropylene. You can see here the two different between these two polymers, only minor change. Only one case has the phenyl group, other case they have the methyl group. Just changing this small change in the polymer backbone, their thermal properties are largely modified. For example, you can see Tg of the polystyrene 100 degrees centigrade and Tm is 260 degrees. Whereas in the polypropylene, their Tg, Tm are 0, 160 degrees respectively. So you can see just changing the polymer backbone, small atom, their properties are completely changed. The difference nearly 100 degrees centigrade. So that much of the change you can see by changing the minor change the structural property of the polymer backbone. And not only the change in the monomer type, also within the same polymer, by changing their arrangement, type of arrangement, they can also bring the huge change in the macroscopic properties. For example, you can see polystyrene. You can take a polystyrene, the pentans, that is the phenyl group, that can be possible in three different ways in the polymer backbone. One case, all the phenyl group, they can arrange one side with the rest of the polymer chain. That is called isotactic polymer. In second case, the phenyl group like a alternate, one case in the top, other in down, top down, like alternate way. This kind of arrangement is called syn-diotactic polymer. In third case, they can be like a randomly. There is no any particular order. Those kind of tacticity is called atactic polymer. Now you can see the just arranging the phenyl groups in the different way, their macroscopic properties completely changing. First two, isotactic and syn-diotactic polymer, you can see they have some kind of order, well-ordered structure. In the one case, they have one side with the polymer chain, other case they like alternative. Because of the order arrangement in this polymer backbone chain, these two polymer can exhibit the semi-crystalline phases. Semi-crystalline, like a mixture of amorphous and crystalline. These kind of polymers are called semi-crystalline polymer. Whereas if you take the attractive polymer, in this system, the phenyl groups are randomly arranged in the polymer background. Due to randomness of these arrangements of phenyl group, this polymer cannot exhibit the semi-crystalline. This system always in the amorphous only. So now we understood the difference between the effect of the phenyl group arrangement and their physical properties. So if the polymer chain has the regular arrangement of the backbone, that can exhibit the semi-crystalline. If it is random, it remain amorphous only. Amorphous. The difference between the amorphous and crystalline can be understood by looking this photograph. Okay, coming to the difference between the semi-crystalline polymer. Why semi-crystalline polymer is so important over the amorphous material? Because the semi-crystalline polymer exhibit the extraordinary physical properties like good mechanical properties, barrier property, electrical properties, solvent resistivity, and very good thermal property compared to the amorphous polymer. Because this crystalline phase acting as a pillar for the improve the overall property of the polymer. Because of this one, the semi-crystalline show extraordinary physical property over the amorphous polymer. So because of this superior property of the semi-crystalline polymer, we always prefer the semi-crystalline polymer in the commercial material application instead of the amorphous polymers. Okay, next coming to the polymer crystallization. Crystallization is nothing but the process of change from a random system to order system. That is called crystallization. The crystallization is a process completely different from the small molecule to polymer. In the small molecule, the crystallization is very simple because of the smaller molecule have a very low energy barrier, so they can crystallize completely into well-ordered structure, completely 100% like a single crystalline. For example, you can take a water can form smaller molecule, they can form single crystalline. Whereas if you take the polymer, it is a very long big chain molecule. This polymer has a complex entanglement. Due to that, this polymer cannot form a completely crystalline. Instead, they form a semi-crystalline, as we shown the schematic of the semi-crystalline polymer. So that is the major difference between the small molecule and polymer, their crystallization process. Okay, coming to the next one, the crystallization process in the polymer material. Yes, the crystallization start from the random system, that is the amorphous polymer. These amorphous polymer, by given some external force, by anything by thermal or solvent induced or mechanical force, these energies they can induce the chain mobility in the chain mobility. These chain mobility slowly eventually form induce the crystallization that form a smaller crystallite. This smaller crystallite eventually act as a nucleation for the further growing to bigger structure, that is called lamellae. These lamellae further grow into macro structure that is called spherulite. So these sequential phase transition from the amorphous to the crystalline can be studied by using the different technique. These smaller structure, smaller crystal can be studied by using the wide angle X-ray scattering, and a lambda kind of structure can be studied by small angle X-ray scattering, and micro spherulite morphology can be using the polarized optical microscopy. So using all these techniques, we can see the sequential change from the amorphous to crystalline. So this is the process of the crystallization, the polymer material. So hope you understood about the little bit physics of the macromolecule. If you have any questions on this one, please let me know. I can explain this one. If you don't have any question, let's move to the main topic. So today the main topic is a functional nanoporous crystalline polymer films. The porous is one very important functional in the material science. These porous metal widely used in some of the functional applications like membrane, gas storage, and separation material, and catalysis, tissue engineering. So these are some of the applications of the porous material. Some of the applications of the porous material. Here, the big question coming to us: what kind of porosity really has the functional application? So porous valve that can be have a different kind, but which kind of porosity, like a micro or nanoporous, really important this one. So before going to answering that one, we can see the classification of the porous material. Porous metal can be classified into three categories. Those are like a macroporous, mesoporous, and micro or nanoporous material. So depend on their pore volume. If the material has the porous volume more than 50 nanometers, those metals are considered the macroporous material. And the second one, mesoporous, they have the porous film between the 2 to 50 nanometers. Those are comes under the mesoporous material. And third one, micro or nanoporous, they have the porous film less than 2 nanometers. These kind of materials are comes into the microporous material. So here coming to the our question, among the three systems, the microporous material has a very small porous volume. Due to small porous volume, they have the high selectivity in the molecular sensor, many of the applications. So due to high selectivity of this one, the nano or microporous materials are very fundamental interest. So we are also interested in the macroporous material in our studies. So coming to the nanoporous material, so that can be the library of the material. So you can see some of the microporous material like a zeolite, metal organic polymers, covalent organic polymers, polymer organic polymer, and some of this list one. So these are some of the known nanoporous material. So among these porous material, we are mainly interested in the porous organic polymer as a polymer chemist. So coming to the porous organic polymer, they can be again two kinds. One is the thermoset polymer, the second is thermoplastic polymer. We know what is the difference between the thermoset and thermoplastic polymer. We are mainly interested in the thermoplastic nanoporous crystalline polymer. Why we are interested in the thermoplastic nanoporous material? Because these thermoplastic nanoporous polymer, they have the unique kind of porosity, like a cylinder, like a cavities or cylinder, and with the unique porosity in the pore volume also. Because of all these one, these metals are already being used in some of the functional applications like a molecular sensor, gas storage, water and air purification, and active packaging applications. So some of the application of the nanoporous material. Coming into the preparation, how to prepare the nanoporous material. So this can be simple by we can prepare the nanoporous material starting from their co-crystalline phases. Yeah, co-crystalline phase nothing but it is a complex between the long chain polymer and a small molecule, small solvent molecule are called co-crystal. From this co-crystal, by remove the guest molecule, guest extraction, they can form a nanoporous co-crystalline polymer. But it's a very rare phenomenon. Many of the co-crystalline pairs, by removing the guest molecule, they become amorphous only, amorphous. But very two specific polymer, they can form a nanoporous crystalline polymer. By extraction of the guest from this co-crystalline phase, they form a maintain the crystalline phase, and within this crystalline phase, they maintain the porosity. So those kind of materials called nanoporous crystalline polymers. So coming to the, as I mentioned, the only two polymer exhibit the nanoporous crystalline polymer. The first one is the syn diatotic polystyrene. The second one is the poly 2,6-dimethyl 1,4-phenene oxide. Only these two polymer known to exhibit the nanoporous crystalline polymer. And both are luckily are commercially available. And coming to the nanoporous crystalline polymer. First, how to identify the nanoporous crystalline polymer? This can be simply identified by measuring the density value. Generally, the density of the semi-crystalline polymer has its corresponding spectrum. The density is density of the amorphous phase more than their crystalline phase. So that confirms it is a nanoporous crystalline polymer. For example, you can take a polystyrene, synthetic polystyrene. The density of the amorphous is 1.04, and its corresponding semi-crystalline polymer is less than 1. So this confirms it's a crystalline nanoporous material. And the second polymer, that is a PPO. These PPO amorphous phase, the density is 1.0.4, whereas its corresponding crystalline phase, the density lower than 1, only 0.98. So this confirms it is a crystalline nanoporous material. So coming to our interest in these two nanoporous material, we are mainly interested in the PPO polymer because this is a very special polymer. It has a very good thermal properties, and TG and TM, they have more than 200 degrees centigrade. And moreover, it has a porous, both crystalline and amorphous. So that's one of the reasons we are mainly interested in the PPO polymer. So presence of this porosity in amorphous has been discovered by Professor factor in the 1969, and the presence of crystalline nanoporosity, it is recently discovered by Professor Daniel et al. in the 2021. So this confirms the porous, crystalline, and amorphous. For the confirmation of the presence of porosity in the crystalline amorphous, recently Professor Daniel, they studied the vapor phase option of the CCl pore at a different activity, at a different relative pressure. You can see these are relative uptake of the CCl pore with respect to the polymer weight. The polymer, you can see pure amorphous PPA polymer, they also show some sorption, nearly 8% with respect to the weight with respect to the weight percentage. Whereas the PPO semi-crystalline polymer, it's so higher than the amorphous. So that confirm PPO is a porous, both crystalline and amorphous. So that is the first confirmation. PPO is a porous, both crystalline and amorphous. For the clear-cut confirmation, we also studied this one. For the comparison, we are taking the 3 different polymer, PPO, SPS, and polyelectric polymer. For these studies, we choose the different vapor molecule, that is perchloroethane, and we studied the sorption at a very low activity, 0.01. For example, you can see that there PC weight uptake. The PPO show the highest sorption, followed by SPS, and very low or negligible in the polyelectric. So this confirms that one. PPO definitely it is a porous, both crystalline and amorphous, and SPS is only crystalline porous. It's known in the literature. And PLLA, you can see there is no any sorption. This confirms PLLA is a dense, both crystalline and amorphous. So this study clearly confirms PPO surely it is a porous, both crystalline and amorphous. Coming to the PPO powder, the Professor Daniel, they characterized this PPO powder, semi-crystalline powder, with a very high surface area, 550. These surface area very huge. These surface area are mainly contributed by nanoporous crystalline phase. Nanoporous crystalline mainly contributing this one. So this beta surface is nothing but it is mainly studied by nitrogen sorption. By nitrogen sorption at isothermal condition, you can obtain these values. These beta surface mainly obtained starting only from the nanoporous pores only can contribute these values. For general polymer film, they have the highest beta surface area only 40 meters per grams only. But this powder show 550. So this completely new kind of polymer. This polymer with the high surface area. Okay, now we have seen the importance of the PPO polymer, of their surface functional property and porosity and thermal properties. But till now, all these studies happen in the powder state. Powder state applications are very limited, cannot use for the broader range of application. And moreover, these powders are recycling also very, very difficult. And sometimes these powders are easy to leak into the environment. So that makes a high plastic pollution. Here, our objective to bring all these surface function to polymer film, bring it to the polymer surface. In this way, in the polymer state, applications are very huge, where you can extend a very broad range of application, and also recycling also very easy in the film, and also where we can avoid the plastic pollution. So that is one of our idea. For this one, recently we developed one new processing method. We able to prepare a polymer film with a very high surface area, that is more than 620. So these surface area more than the powder, so this is really surprising. Generally films have the beta surface are very negligible, only four only, but these films so very huge, more than its powder. So these are really completely surprising results. And you can see the density of this one, benchmark film, it's so 0.99. But our film show also near to this one. So this confirm this film definitely is a film only, but surface function properties are completely different. These difference in this surface property mainly due to it has a unique kind of marble, that is fibrillar marble. That is mainly driving for the high surface area of this one. And other interesting thing, important observation, this one. Compared to their aerosol, our film shows a very high surface area. Till now known, the aerosols only expect the highest surface area, 550. But our film surpassing their surface area, that's more than aerosol and powder. So this kind of the film with the surface functional property completely new. So this method recently we documented a US patent. Also it appeared in some of the important publications. Okay, coming to the application of this new high surface film, we are trying to make use as a air purification application. For this one, we tested the PC, perchloroethane sorption, at a very low activity. For comparison, we also tested with the aerogel and benchmark film. You can see compared to benchmark film, our film show very fast sorption kinetics and large amount of PC uptake compared to this benchmark film. So these are completely very good and even far better than the aerogel. So this kind of, till now, aerosols are best known material, the sponge kind of material, but our film completely overtaking the aerosols. So these are really very excellent performance of our film. And also other important property in the real world application, mass to volume ratio. Mass to volume ratio compared to the aerosol, our film show nearly 8 times larger uptake compared to the aerosol. So these are also other interesting parameter of our new film. And also we studied the diffusivity with the benchmark film. Compared to the benchmark film, our film show nearly 400 times faster diffusion the polymer film guest molecule compared to the benchmark film. So they are also a very excellent property of this new film. And coming to the recycling, for understand this one, we tested the cyclic stability, like 5 cycles of sorption, desorption. You can see even 5 cycles of sorption, desorption, their PC weight uptake remain unaltered, maintain their efficiency without any changing. Whereas in the aerosols, you can see after 5 cycles of sorption, the sorption and desorption, the desorption performance is reducing with the cycle. So that confirms PPF film is the high surface film is very good. You can use reusable, recycle without any change in their performance. So these kind of metals are very important, and their performance are very needed for the real world application. Also, we studied the mechanical property of this polymer film. Bendability in order to see really it is a mechanically stable for the some of the application. And these bendability test, we compare the amorphous film. You can see compared to the amorphous, this film exhibits a little bit brittle in the nature, but this much of brittleness is sufficient enough to use the commercial application. So these are manageable in this kind of brittle nature. And thermal stability, in order to understand the thermal stability of this polymer, we analyze this high surface film, also benchmark at a different temperature in the range of 50 to 200 degrees centigrade. And we tested the corresponding film bead surface area and degree of crystallinity. You can see from this study, at least 150 degrees centigrade, they maintain their surface area as well as the crystallinity. Not much reduction happen. Only above 150 degrees only we can see the drastic reduction in this one. Sorry for interrupting. Okay. Even after thermal handling, you can see after 200 degrees centigrade only the reduction. So from this study, at least this will higher temperatures up to 100 degrees without any change in their performance. Okay, these are all about the high surface film, their related new application. These findings are completely new. Okay, coming to the next interesting topic, that one, transparent planar oriented nanoporous PPA film. First, planar oriented is nothing but it speaks about the crystalline phase anisotropy. Generally, polymer film can exhibit the two kind of crystalline phase anisotropy. One is a C perpendicular. Here, the crystalline chain axis they are perpendicular with respect to the film plane. This kind of crystalline anisotropy is called C perpendicular orientation. And the second kind of planar orientation, that is C parallel. Here, the crystalline chain axis they oriented parallel to the film plane. So this kind of planar orientation is called C parallel. And third one, this anisotropic mean unoriented crystalline phase. So these are the two different kind of crystalline phase anisotropy you can see in the polymer film. So these are about the planar orientation. Here the surprising results, by changing the crystalline phase anisotropy, we observed some unexpected optical transparency. Mainly the C perpendicular. You can see the C perpendicular, it looks like very transparent. The transparent, it looks like a amorphous only. Whereas in the C parallel film, it looks like a opaque in nature. So the same polymer, the same crystalline phase, just changing the crystalline phase, we observe the difference in their optical property. So this difference also can be seen from the UV visual spectroscopy. You can see this one. The amorphous and C parallel, they transmit close to each other, followed by unoriented and C parallel. So this kind of change in the optical property, change in the crystalline phase, completely new finding this one. So these difference in the optical property, we are mainly interpreted by represent. This PPO polymer comes under the positive birepresentative polymer. In this positive birepresentative polymer, C perpendicular orientation, this optical ellipsoid, it is oriented perpendicular film plane. In this direction, the refractive index of the polymer, it is very high, that is equal to close to the amorphous polymer. That is the reason the C parallel, C perpendicular, and amorphous film, they looks like a very transparent. So this is the interpretation we interpreted from this finding. For example, if you take the negative birepresentative polymer, their optical properties, it will be completely different. It will be opposite. For the comparison, recently we studied this with the different polymer. Example for the negative birepresentative polymer, polystyrene, syn-dioxide polystyrene, and the positive birepresentative polymer, as you know, PPO. And we trying to understand the optical property. We prepared the planar oriented film, both SPS and PPO. You can see C perpendicular oriented. SPS film is a negative birepresentative polymer. It's opaque in the nature. Whereas in the PPO, you can see it is a transparent. Whereas if you take the C parallel orientation, SPS is transparent and PPO is opaque in the nature. So our interpretation on the birepresence phenomena, it is true only from these studies. So all these findings, studies detail, you can find from these articles. And these related finding, optical property, recently appeared as the front cover image in these important journal in the RS publication, that is material advances. So these are all about the planar orientation and optical transparency of the planar oriented nanoporous film. So next, coming to the other important property of this planar oriented nanoporous film, we observed the change in the kinetics of the vapor sorption. For this one, we tested the perchloroethane vapor sorption at low activity between the C parallel and C perpendicular. You can see compared to C parallel, the C perpendicular show very fast kinetics of sorption and a large uptake compared to the C parallel film. And the difference between these two films, the diffusivity nearly 40 times. So same polymer, same crystalline phase, same density, but their difference between the diffusivity completely different. The difference is 40 times. So this completely surprising, this one. And also other advantage of this film, these are also mechanically stable, this film, and is also good transparent and faster uptake sorption, and mechanical also this good film, this one. And other application, this planar oriented film, we observed this one, kinetics of sulfonation. Before discussing about the kinetics of sulfonation, let us see the importance of the sulfonation film. Sulfonation films are very important in the battery application, mainly cation exchange membrane, widely used this one. So in the general procedure, the traditional method for this film preparation by solution state sulfonation, this solution state sulfonation always lead to amorphous, highly degree of sulfonation. But these films, amorphous sulfonated films, are very poor hydrodynamic stability and ethanol resistivity. You know, many of these ionic exchange membranes, they operate in the very high hydroscopic condition, high temperature. But in this particular condition, these amorphous sulfonated films are damaging this one, not stable. But for this problem, we recently identified new method. We prepared a sulfonated new solid state sulfonation. This way, we are able to get the polymer with the sulfonation and semi-crystalline sulfonated film. These films are very good stability towards the hydrothermal stability, water uptake, and ethanol resistant. So this film, these additional stability mainly due to this crystalline phase. This crystalline phase acting as a pillar for the stability in the sulfonated phase. So that is the main reason the solid state sulfonated semi-crystalline sulfonated films show very good stability towards the hydrothermal and ethanol resistivity. These are very important contribution in this field. Also, coming to other important results, kinetics of solid state sulfonation. Here the C perpendicular show very good fast degree of fast sulfonation compared to C perpendicular rotation. Also, it offers a very good high degree of sulfonation between the two systems. And moreover, we also noted some important observation, that degree of sulfonation uniformity. Here I have shown the scanning electron microscopy edge image and the corresponding EDS spectrum. You can see EDS spectrum is a sulfur distribution that indicate that sulfonation uniformity. In the C perpendicular film, you can see the degree of sulfonation very uniform. Whereas in the case of C parallel, the sulfonation not uniform. Only edges only you can see the high degree of sulfonation. In the core it's not happen. So from these studies says that one again C perpendicular film is a very efficient candidate for this kind of application. Coming to the other application of this planar oriented film, guest thermal rays from the planar oriented co-crystalline phases. Here the important observation, we noted that one, we trying to understand the guest molecule rays from their co-crystalline phase. These are TJ thermogram. We can say pure liquid molecule. It's evaporating at 200 degrees centigrade. Whereas in the case of co-crystalline phase, C perpendicular and C parallel, they show completely large difference in thermal stability. One case, the guest molecule evaporated at 150 degrees centigrade, whereas in the C parallel, the guest evaporated very different temperature at 275 degrees centigrade. So the same polymer, just change the planar orientation, the difference in the guest removal completely different. The difference is more than 100 degrees centigrade. So this kind of phenomena, it's really surprising, this one. For the same thing, we also tested for the other molecule, very volatile molecule. Here we're choosing the guest molecule, that is trichloroethane. This is a very volatile molecule. You can see even at room temperature, it is completely evaporating. Whereas in case of the co-crystalline phase, the TCA, this trichloroethane molecule, is very stable, and stability has been increased more than 180 degrees centigrade. So this much thermal stability increasing in the co-crystalline phase, that's really surprising, this one. So this is a completely new kind of study, this one. So the new kind of study. Okay, previously we discussed about the importance of planar orientation, the relative application. So let's now discuss about the procedure for applying this planar oriented nanoporous film. This planar oriented nanofilm can be obtained starting from the amorphous by guest-induced crystallization. These process can be obtained for the planar oriented nanoporous film. So first, before going to discuss about the procedure, let us see how to characterize these planar oriented nanofilm. So this can be studied by two-dimensional wide-angle X-ray scattering. By using this technique, you can understand the kind of planar orientation. Planar orientation. For example, first you can see this image. You can see pure rings. There is no any kind of pure rings. This kind of typical X-ray pattern indicate the unoriented isotropic system. Instead of rings, if you can see some kind of arcs, these kind of arcs indicate that they have some kind of crystalline phase anisotropy that can be planar orientation, and both have the like arcs, and confirm it is a planar oriented films only. Now between these two systems, how to identify the C parallel and C perpendicular crystalline phase orientation? For this one, very easy to understand by identification of the crystalline plane chain axis, that is a 0, 0, L plane. If the 0, 0, L plane, it is in the equator, and 𝐻𝐾0 plane in the meridian, this kind of reflection pattern indicating for the C perpendicular orientation. In other case, if the 0, 0 plane, crystalline chain axis plane, the meridian, and the other 𝐻𝐾0 represent the equator, this kind of typical reflection for the C parallel orientation. So by using this X-ray pattern, by identification these mainly 0, 0 plane, you can identify the kind of crystalline phase anisotropy. Okay, coming back to the procedure. These, as already mentioned, by using the guest-induced crystallization, we can obtain the planar-oriented nanoporous film. So that can be using the selective guest molecule with the diffusion at particular speed. If the guest-induced crystallization, the guest diffusion, if we follow this particular speed, slow diffusion with the lower than this particular speed, we can obtain the C perpendicular oriented nanoporous film. In other case, if the guest diffusion, if you control more than this particular speed, so that case you can have the polymer with the C parallel orientation. And other than these two, if you follow that guest diffusion between these two speeds, we can have the isotropic unoriented crystalline phase. So these are the simple procedure for controlling this one. Okay, coming to the film thickness dependency perpendicular orientation, the PPF film. Yes, you know, the previous discussion method, very general procedure. those processes are you can see the degree of orientation, the different thickness and the degree of orientation. The thin film, they cannot make a completely, they cannot form a C perpendicular, only unoriented. Whereas on the thick films only can expect the C perpendicular orientation. Yes, you know, the C perpendicular orientation films have a very good application, but the thin films are not possible. You know, many of the commercial application, thin films are highly preferable, less than 20 micron. But our procedure, general procedure, not possible, not possible. Here you can see these are the procedure for technique. These are formulas you can use for the degree of orientation calculation. And you can see here the relation between the film thickness versus the degree of orientation. The thick film, more than 50, you can see the more than 50 micron films only, you can have that C perpendicular orientation. Only thinner film, less than 20 meter, it's not possible. But these kind of films are really useful for the commercial application. Here, our objective to control the C perpendicular orientation, the thin films. Recently, we developed four new technique. Some of them are here. You can see using the selective binary solvent, or using the low temperature gas crystallization, or using the selective interfacial gas crystallization, or using the theta solvent at 40 degrees centigrade. We can have the high degree oriented C perpendicular thin films. You can see, irrespective of film thickness, we can have always have the high degree of orientation, even for thin film, less than 10 micron. So these are really very efficient, very potential technique for the obtain the thin C perpendicular oriented nanoporous film. So you can see the relation here. We drawn this one, the film thickness versus the degree of orientation. All these new techniques, you can see, irrespective of film thickness, we have high degree of orientation. Whereas in the general, the known procedure, only these are applicable for only thicker film above 50 micrometer. So these are other interesting contributions in the field of planar oriented film, planar oriented nanoporous film. These are all the four methods. Recently, we documented the patent this one. So this is a complete about the topic of the planar orientation, their application and their procedure. With this, move to the other fundamental study of this one. Yes, we discussing is a PPO is a nanoporous, crystalline nanoporous film. But many of the fundamental questions are not known in the literature. Here the first question: what is the porous volume, and how these porous are oriented with respect to the polymer chain, and what kind of symmetry these are, like a cavities or cylinder? It's not known in the literature. These are really, we felt like a good opportunity for studying this kind of fundamental study. For answering this one, we trying to understand by three different approaches. The first problem, that is a pore volume. For understanding the pore volume, we prepared a co-crystal with different guest molecules. They have the different molecular value in the range of 123 to up to 350 degrees centigrade. And we, from this co-crystal, we extract the guest molecule from a nanoporous co-crystalline phase. Now, here our interest to study the melting temperature, all these nanoporous crystalline phase obtained from the different guest molecule. We observed some trend in the melting temperature. You can see they like a turned U-shape symmetry. So these are really a very interesting trend, this one. For understanding this one, we drawn the correlation between the melting temperature versus the guest molecular volume. You can see we observed some inverse U-shape symmetry, and particularly this group of molecule we show very high melting temperature. And below this one, you can see the drastic reduction. From this study, we interpret data that one. This particular group of molecule, they are best fit in the co-crystalline phase. As a consequence, they form a stable nanoporous crystalline phase. That's the reason that from this interpretation, we understood that definitely this PPA film has the porous volume in the range of 150 to 200 angstrom cubes. That is the first question we answered this one. The second one, pore symmetry. For understanding this one, we are trying to understand by axial stretching the co-crystalline phase. For this one, we prepared a co-crystal PPO with the co-crystal the decane long chain molecule, and we prepared axial stretching and studied the polarized FTIR spectroscopy. Here we observed some surprising, interesting results. They observed some polarization in this one. Polarization in the guest molecule. These guest molecule, they oriented parallel to the stretching direction. stressing that this confirm that one. Definitely, this PPO has the cylinder kind of porosity. Cylinder kind of porosity. And third, that question that for distribution, for understand this one, we studied the PC vapor sorption and we compared between the C parallel and C perpendicular. Already we discussed the same in the previous slide. The C perpendicular is a very good sorption and larger uptake compared to C parallel. So this study confirmed that definitely the pore this cylinder definitely they were parallel to the crystalline chain axis. So that's the reason the C perpendicular films are very good sorption. So overall, all these three studies combined gives the conclusion that definitely this PP film has the cylinder kind of cavities with the pore volume in the range of 150 to 200 angstrom, and this pore it's worried along the chain axis. So these are conclusion. And other important conclusion from this one, this polymer film is a intra-helical nanoporous material. Intra-helical nanoporous. So these are the fundamental fundamental studies in the PPA polymer, their porosity. Next, coming to other fundamental study, the crystalline phase. This PPO film, we characterize with the three different crystalline phases. Those are we named ourselves and we found this one. We named as a alpha, beta, and gamma crystalline phase. These two phases, particularly these two phases, like they have like a monoclinic unit cell. They have the different zero periodicity. And whereas in the third one, gamma phase, it's a mesocrystalline phase. It doesn't have any all the parameters. This one, and among these three systems, you can see their crystalline density are less than 1. So this confirms these two films only nanoporous, whereas the gamma phase, the density more than 1. So it is not a nanoporous crystalline polymer. For understanding from this one, you can see alpha, beta, they are in the surface of the water, whereas in the amorphous and the gamma phase, they are in the bottom of the flask. That confirm they are not a nanoporous. These only two polymers are a nanoporous crystalline polymers. And also we study the phase transition among the three crystalline phase. They can phase on from one phase to other phase by using the different gas to molecule. So these are about something about the crystalline phase and related fundamental contribution. Yeah, with this coming to the conclusion that using a suitable gas to crystallization, the PPO can be obtained with the novel functional properties. One case we can obtain the film with the high surface area. These films show superficial bed surface area, fast sorption kinetics, and mechanical also very stable, thermally also stable. These kind of materials are really used for the super solvent material application. Whereas in other case, by in this other condition, we can obtain the film with the C perpendicular orientation. These film have some unique properties like a very transparent, fast sorption kinetics, mechanical stable, and fast chemical reactivity. So these are other advantages of the planar oriented film. Hopefully, these films can find some potential application in the near future. And the fundamental study also we are able to answer some of the fundamental questions like this film is a this PP is a nanoporous polymer with the cylinder kind of cavity or in this particular range, and all these are oriented parallel to the chain activity. So these are other important contributions in the field of PPO polymer. So these are all about the conclusion. Coming to the contribution to the polymer science, I documented 4 patents, 45 publications. These are presentation for the conferences. And I sincerely thank you, all the supervisor. First one, my postdoc supervisor, Professor Gaetano Guevara. He's the boss, my boss. He's a very special man. He's a student of Nobel laureate. His name Professor Natta. He's the first one to receive the Nobel Prize in the polymer chemistry. And the second one, my PhD supervisor, Dr. 𝐀𝐲𝐬, is a very famous scientist in India. He's currently working in the CSN in Thiruvananthapuram. And also I thank you, my team manager, Lydia Teruzzi, Prysmian company. Also I thank you all the agents for their final support. Also thank all my friends. Finally, thank you for your patient listening, for your time. Hello, madam. My presentation has finished.
Sir, good evening, sir.
Yeah, good.
Sir, participate, there is no asking the question, sir, queries. So now it's vote of thanks by Dr. Haripriya Madam, sir, convener of our
Okay, sir.
FDP.
Any comments? Any comments about my presentation? Any discussion if you need? Okay, I'm happy to discuss with you.
Good evening, sir. On behalf of
Good evening,
Department
madam.
of Technology and Humanities and Basic Sciences, I, Dr. G. Haripriya, Professor of and HOD of HNBS, would like to express our heartfelt thanks for taking the time to share your expertise with us today. Your lecture on functional nanoporous crystalline polymer films was truly enlightening and provided valuable insights into the latest advancements in the field. We are glad and appreciate the effort you put into making complex concepts assemble to our students and faculty, and for inspiring us with your passion for research. Thank you once again, sir. Thank you so much.
Yeah, thank you, madam. Thank you once again for your opportunity.
Thank you.
Yes.
Good evening, sir.
Good evening. Hello, can you hear me?
Yes, sir. You're audible, sir.
Okay, good. Thank you.
Now we'll start the third session. It's a great honor to introduce today's keynote speaker, Dr. Murali Yallapu, who is a tenured associate professor of Department of Immunology and Microbiology, Medicine Oncology ISU, and member of South Texas Center of Excellence in Cancer Research at the School of Medicine, University of Texas, Rio Grande Valley. He has obtained postdoctoral training in material science, drug delivery, nanomedicine, and cancer biology from Cleveland Clinic, University of Nebraska Medical Center, Sanford Research. Served as assistant professor at the Department of Pharmaceutical Sciences. His contribution as editorial board member for various delivery, nanotechnology, and cancer-related journals have earned a good name in the community. Sir has also been an ad hoc reviewer for NIH and various national and international funding agencies. Sir has published over 200 peer-reviewed articles and reviewed in journals, book chapters, and over 155 conferences abstracts. His work was cited over 17,806 times with an H index of 67. His passion for research currently focused on development of nanomaterials for biomedical applications. To add on, his keen interest in cancer immunology has generated effective nano formulations for cancer immunotherapy. It's our pleasure to have you here, sir, as our resource person, and I request to please take over the sessions. Thank you, sir.
Thank you. Thank you so much. So good evening, everyone. Can you hear me?
Sir, you are audible, sir.
Yes, sir.
Okay.
Yes, sir.
Good. Wonderful. Thank you. So let me share my slides. Okay. So slides are viewable at your side.
Yes, sir. Visible, sir.
Yes, sir. Visible, sir.
Okay. So just, okay, good. And they're moving, right?
So no, sir, slides.
Yes, sir.
Yes,
They
sir.
are moving.
Okay. Yes. So good evening, everyone. Today I try to give you information related to therapeutic nanomedicine for cancer therapy and image applications. Yes. So is the slides are moving from your side?
Moving, sir.
Okay. Yeah. So just before I go in detail about this topic, just I want to introduce about my laboratory over here in the University of Texas, Rio Grande Valley. And my lab specifically focused on various applications that includes imaging prevention, therapy, drug delivery and gene delivery, and diagnosis and theranostic of various type of nanomaterials. That particularly we are focusing on cancer therapeutics. So that is my prime area. All my lab people, they do in this one of these areas. But apart from these, like we also collaborate with other faculty and laboratory where we develop some of the strip-based assays for rapid test purpose, for example, COVID, or maybe we also develop some of the nanotechnology-based immunotherapy or immunoimaging applications. If you see, there are two areas that we focused on, particularly using nanomaterials for cancer therapeutic application. Other one is developing some of other nanomaterials for various other applications. So my topic, divided into two areas, two sections, where I would be giving more details about what is cancer and how nanotechnology being utilized for cancer therapeutic application. That is basics. Then I would go ahead and provide you more information about how many types of nanomaterials being used for cancer therapeutic application that are approved by FDA, and what are the associated side effects are there with the conventional chemotherapy, how we can make a better therapeutic regimens for cancer therapeutics. I will be discussing more about those type of materials in section 2. Okay. So what is cancer? Why we are particularly interested in doing cancer research over here. So if you see this slide, so there are close to 1.9 million people are diagnosed duly with various type of cancers that is recorded in 2021. At the same time, in the same year, there are about 600,000 people have been died related to cancer-associated deaths. So that means there is a critical need that one needs to work on this cancer area so that you may either develop early cancer diagnosis, or maybe you can develop monitoring the disease, and also maybe you can develop a better therapeutic regimens for cancer therapeutics. All right. So in general, whenever we talk about cancer, how many ways you can manage this cancer. Okay, prevention is the primary aspect, like where you can take a caution in diet. Maybe you are exercising, maybe you are not taking alcohol or smoking. Those are falls under your prevention category. So whereas screening protocols, for example, cervical cancer, you do regular pap smear, or maybe you undergo colonoscopy for colon cancer. Maybe you undergo breast examination or mammography every 2 years or 3 years using either imaging technology or by self examination, or maybe a doctor prescribed testing. And the other case, once you know that you have been diagnosed with cancer by various imaging modality, or maybe by simple examination by a doctor, then the treatment protocols will takes place, right? So where you can apply chemotherapy, radiation, and so on. So where I would be talking more about treatment regimens of various things, and then particularly how our nanotechnology can be implemented in treatment area. So you all might be knowing that how many ways the cancer can be treated. The first priority would be surgery, where you can remove all the tumor tissues or the tumor cells from the body, okay, and that includes a lymph node elimination, okay. So where, if you remove this tumor tissue, so you don't have any other tumor cells left there that can grow further, right? So therefore, it considered as a best therapeutic option for cancer treatment. However, this treatment or the surgery is only limited for the primary tumors. So, there are some of them are primary tumors, some of them are metastasized. Okay, you know what that means? So primary tumor means breast cancer means that is originated from the breast and it is still localized in the breast itself. But after some time, what happens if you don't diagnose that early stage, the breast cancer, the tumor cells in the breast, they can travel in the body and then they can go into other part of the organs, for example, to the brain and maybe a liver or maybe a lung. Okay. Same way prostate cancer. Prostate cancer can also be like, go to the bone, brain, and a few other organs. So those kind of like metastasized tumors may be not efficiently removed by surgery because there may be so many tumor masses at different parts of the body. So that means you have a limitation there. Then you followed with the radiation therapy, right? So surgery is not a best option for some of the cancer treatment. Therefore, the radiation is another option. But radiation is simply kills the cells by DNA damage, where the curation of the treatment it's based on it cannot kill the bulk tumors, right? If it's a tiny tumor, it is the best option to use radiation therapy, right? There are two versions of the therapy that are widely used and they are best therapeutic options. Okay, one is surgery and another one is radiation. Radiation can kill only tiny tumor cells. Surgery can be removed only bulk tumor, but those should not be a metastasized or the smaller tumors because for small tumors you don't do surgery and then remove the smaller parts of the tumor cells, right? So then the third option, the best option could be a chemotherapy, right? For example, like you remove tumors by surgery or surgically. So where there might be leftover smaller tumor masses or tumor cells, right? If you give a chemotherapy, that will also be killed by chemotherapy. Another example, like radiation therapy, you have a radiation, like it can kill only the tiny tumor, or if you give the radiation on the bigger tumor, maybe they will be shrunken, but that will not be a cure, right? Then you apply chemotherapy. What that means in general, the cancer treatments might be combination of surgery and chemotherapy, or maybe a radiation and chemotherapy, or maybe surgery and radiation. It's a combination of a couple of different type of therapy. Okay, then why we are interested about chemotherapy, right? So we are interested in the chemotherapy because the drug molecules, whatever we develop for cancer therapy, they may not be very specific to the cancer cells. For example, if you take any drug, they not only kill the tumor cells, but also they doesn't distinguish on the normal cells. That means the drug molecule, it acts on the tumor cells as well as the normal cell. Same way, that means like, even they kill the normal cells also. So therefore, you may see a lot more systemic side effects when you use a chemotherapy. So therefore, we want to make sure that your drug can go to the only tumor cells, not the normal cells. So therefore, nanotechnology come into the picture how better we deliver only at the tumor site. Well, so whenever you think about nanotechnology or nanomaterial that we want to use for chemotherapy application or cancer therapeutic applications, we should know that, what are different type of nanomaterials that are exist. Is that nanomaterial only used for drug delivery? That's a question, right? So it's a genuine question by everyone, right? So in general, nanomaterial, you can make any type of nanomaterial from the metals or metal oxides. So you can create a nanomaterial, or maybe take any polymer material, then you can make them into a nanomaterial, right? Depending on the material that you make with the parent molecules, polymers or metals, then you can apply for various things. For example, like the same polymeric material can be used for drug delivery. Same material can also use for detection, diagnosis, and the same materials can also implement as a mechanically altered material. For example, when you fill some of the fillers in the concrete, you can make even more stronger that particular construct. Okay, for example, like you are mixing with some cement with the tiny particles to improve the mechanical strength, right? Some of the nanofibers you can introduce in the aeroplane construction of the composite material, then further you can enhance the mechanical strength. There may be different areas that you can apply. Okay, all the nanomaterial. But today, we will be only focusing on nanomaterial that can be used for cancer therapeutic application. Throughout my lecture, you may be hearing or come across some of the terminology such as nanoparticles, nanomaterial, EPR mechanism and active targeting of the tumor cells, and various type of nanomaterials, and polymeric nanoparticles, magnetic nanoparticles, nanogels, and polymeric mice. These are commonly, maybe you might be hearing throughout this lecture today. And what is nanomedicine? I said like nanoparticles can be used for various applications. But when it comes to the nano and medicine, that is nanomaterials that can be used for only medical application. That doesn't mean that only for cancer therapeutics. You can use for various any type of medical related applications. Okay, but according to the NIH, National Institute of Health, National Cancer Institute, FDA, and other standard agencies, so define that nanomedicine related nanomaterial whose size at least in one dimension close to 100 nanometer or less, or maybe in many cases up to micron, we consider them as a nanomaterial. Okay. Well, as a nanoscientist, we might be knowing that, what is the different type of nanomaterial, how they look like, structurally, how they differ one from another. And then if you compare with the, existing molecules, how these nanoparticles can fall in terms of size range, right? So it's a visualization of how we think in general, right? So if you see on the top side of this slide, you can see some of the structure that we laid out right from the glucose molecule to proteins, DNA, viruses, and cellular structure and salt grain and tennis ball. So see the tennis ball is like 10 power 8 times nanometer size. That is like 1 power minus 1 size is a glucose molecule in terms of nanometer size, right? So where our nanoparticles, in general, they fall for therapeutic applications or for various nanomedical applications, those were lying in between virus and proteins. If you take any protein, human serum albumin or any other proteins, the size of the proteins are like somewhere 4 to 5 nanometer, depending on the molecular weight of the protein. Same way like viruses, various number of viruses, if you look under the microscope or maybe electron microscope, you can see clearly the structure of this virus, they may be close to 100 nanometer or a little bit out. So that means all your nanoparticles, maybe if you arrange them, they may fall in this between the range from protein and viruses, okay, depending on your nanomaterial. It could be a polymeric micelle, liposome, dendrimers, metal nanoparticles, such as gold nanoparticles, silver nanoparticles, and quantum dots and polymeric-based nanoparticles. And why, in the first place, we want to use nanomaterials for drug delivery application or medical application? So in majority cases, like you may have a very potent molecule that can kill the tumor cells, but if that drug molecule is not water soluble, okay, it is very hard that can be applied for medical applications, because whenever you take this medication orally or by injection, those drug molecules will be precipitated and then they will be cleared from the system, right? That means you need to improve its aqueous solubility. That's where you can apply nanotechnology or nanomaterial. On the other side, you may have a drug molecule that is water soluble in nature, but the problem could be that is very potent, okay? Before it reaches to the tumor site, but the molecule is very potent, like it will interact with the red blood cell, it will interact with the other epithelial cell. They might have more effect on the normal cells compared to your tumor cells. That means you might need to improve its, systemic toxicity by encapsulating in it, right? So therefore, you can improve the bioavailability and its pharmacokinetics and so on. So where you have a drug that, you take it and then it goes everywhere in the body, at the end, by the time it reaches to the tumor, maybe very less amount of the drug is going to the tumor. Therefore, you have a low targeting ability where that you can improve using nanotechnology. Apart from all these, another issue with the conventional drug delivery is that, whenever we think about chemotherapy for cancer applications or cancer treatment, there are multiple drugs will be given to a patient, not one drug or two drugs, okay? Usually at least one drug, two drug, they will be keep changing the drug for cancer therapy. Why that is needed? Because after certain rounds of therapy with a particular drug, the cancer cells develop resistance to that particular drug, okay? They no longer will be affected by that particular drug. So then they change a different drug, okay? In the cancer treatments, there would be a protocols that exist, like first line therapy, second line therapy, and third line therapy. That's it. So you may change the drugs, only up to a certain number of times. After that, there is no option left to the patient that they can take different type of drugs. The use of nanotechnology will also come to the play here to reverse the drug resistance. So where we can apply our nanoparticles with that particular drug, where it can be taken care of the drug resistance. Okay. So here this slide is not a very educative, but it's like different size of the nanomaterials, how you can imagine. From if you think about 1 to 10 nanometer size, only you can develop some of the dendrimeric nanoparticles or solid metal particles or metal oxides and carbon nanotubes. Okay, these are the only type that you can make in a very smaller size range. Whereas other things like you can make from 10 to 200 nanometer, 100 to 300 nanometer, or maybe 100 to 500 nanometer, various type like polymeric nanoparticles, lipid nanoparticles, and so on. And this is just educating, but only you need to keep in mind that 1 to 10 nanometer, those were good for certain application, a different size range are good for different type of applications in the medical field. Okay. Well, that, maybe you can use nanomaterials for drug delivery applications, and they can solve some of the problems that are associated with the drug delivery, right? Improving the solubility, targetability, drug resistance, and so on, right? But what's the problem that also exists with the nanomaterials, right? So nanomaterials, it's like a same, like, you're taking same polymeric molecules, or you're taking some of the silver salt or gold salt, but you're packaging them or making them very packed, okay? And then you're calling them as a nanomaterial, right? Simply. But once you make a nanomaterial, you can see that. Okay, you can see that, for example, you are making metal salts. From the metal salts, you are making nanoparticles, metal nanoparticles here. In this case, maybe gold nanoparticles, silver nanoparticles. Okay, then you can make a nanoparticle that are aggregated, or maybe you can give a better stabilization with various polymers or other smaller molecule. You can make a very stable nanoparticle that can be used for some amount of the time, maybe a month, 2 months, 3 months, depending on your nanomaterial stability. Okay. Let's say you make a nanomaterial that are not stable enough. Okay, they aggregate. If they aggregate, means like they are no longer good for injection or maybe for drug delivery application or any other medical application. Therefore, always it is interesting to make how better you make nanoparticle, those are stabilized. So you can see the slides, right?
Yes, sir.
Okay. Good. So, as I mentioned, the issues with the drug delivery, particularly nanomaterials, the stability of the nanoparticles plays a major role in drug delivery research. Okay, so here, when you make a nanomaterial, how
Sir?
many ways you this? Yes.
Sorry for the disturbance, sir. Please share the full screen, sir.
Okay, it's not showing you the full screen. Okay, how about now? Is it a full screen?
Please change your slide, sir.
Okay, so how about now? Is it moving?
Not no change, sir. The first slide is there.
Okay, so it's showing only the first slide.
Now it's first slide, sir.
Okay, so I think that.
Yeah.
Now it's cancer statistics, is it, sir? Now
Okay,
it's moving, sir. Now it's moving.
Okay.
Please share the
So-
full screen, sir.
Okay, is it in full screen now?
No, sir.
Yes or no?
No, sir.
So those are not
Please
moving
find
at all.
out F5, sir.
So those are not changing still? Okay. So now can you see the slides that are moving?
Now it's moving in normal mode, sir. Slides are
Okay,
moving in
yeah.
normal mode.
Looks like some technical issue that maybe it doesn't move the full screen looks like. Okay. So maybe I will continue with this. Is that fine?
Okay, sir. Continue, sir.
Okay. Yeah. Okay. So the main issue with the nanomaterials is that you need to provide a better stability to these nanoparticles, where you need to give a better polymeric coating, or maybe use a steric stabilizers to the nanomaterials, where you can have a good solubility, or maybe you can improve the bioavailability of this particle formulation. Here we are showing you at the bottom of this slide, where you can see nanomaterial, like we combined with the curcumin, a drug molecule or natural molecule that is cyclodextrin, and we made a cyclodextrin curcumin self-assemblies. This work was done in 2008, where we simply increased the curcumin solubility in this formulation, and then we applied for cancer therapeutic applications. Next one is like, well, you learn some of the technique and how you can improve the solubility of this drug molecule, but how this drug will be released from the nanomaterial, it's another question, right? So you can see this slide will tell us that there are basically different ways that drug will come out from the nanoparticle matrix by simply diffusion method or maybe a degradation method. Okay, these are the two main drug release mechanism that you can expect from nanomaterials. Whereas in the other case, like, there would be a stimuli responsive drug delivery, right? Where you can see that, you can change the time or you can change the responsivity to the pH. Maybe you can change the responsivity or the environment that where these nanoparticles are going, like maybe thiol responsive, maybe a redox responsive. There are so many ways, like maybe a MMP responsive, metaxi MMP, like metio, some of the fibers that are formed in the tumor condition, where you make a material that when it goes there, you have an enzyme that would release, and then the nanomaterial will be degraded or maybe a peeled off this nano construction, and the drug will be released only at the tumor site. Okay. And as I mentioned before, like, the nanomaterial can follow two ways of delivering at the tumor site. That is, one is EPR mechanism and another one is active targeting. So EPR mechanism means like, it's simply accumulation of the drug molecule that are contained nanomaterials at the tumor site simply by following in the bloodstream wherever they can see the leaky vasculature. Particularly, the leaky vasculatures exist only at the tumor site. These nanoparticles can go into the tumor site and locked up there via this vasculature. Okay, they cannot come back. Whereas the small molecules, so when you have seen the scale, nanometer scale, small molecule like sugar molecule or any other small molecular weight molecules may be up to thousands, okay, up to 1,000 molecular weight. For example, paclitaxel, docetaxel, cabazitaxel, you take cisplatin or 5-fluorouracil or irinotecan, all these drugs, molecular weights very close to less than 1,000 molecular weight, right? These are small molecule. They may have 1,000 times less than your nanomaterial, right? That means if you use only the drug molecule, they can go through these leaky vasculature to the tumor site, but then at the same time, they also come back from the tumor site and they can go back into the bloodstream. So therefore, nanomaterials will facilitate going into the tumor site and locking up there, and then the drug will be released at the tumor site for sustained manner or for a longer time of period. Therefore, all the so far approved FDA formulation, they have this or they obey this EPR mechanism, or they target passive targeting at the tumor site. This is very critical. Okay, so therefore you want to make the particles very close to 100 nanometer in size, where they have access or ability, they can go into the tumor site through this leaky vasculature. Okay. Whereas in the other case, like active targeting, you have same nanoparticles smaller in size, but they are going in the bloodstream, they are going here and there. Maybe even if they go into the tumor site, okay? In the tumor site means like, in the tumors, there are more than, 4 or 5 different type of cells are exist. Maybe fibroblasts, maybe a, stellate cell, maybe a macrophages. There are various number of different type of cells exist in the tumor. Therefore, you need to only hit the tumor cell, right? Where the active nanoparticles, that are active targeting nanoparticles, those just not the nanoparticle, but they have any specific ligand or antibody or any other moieties that are on the nanoparticle. If they reaches to the tumor site, using this passive targeting, they can go inside and then lock up there. But in that tumor site, these active targeted nanoparticles, they only specifically bind to the tumor cells. Then the drug will be released to only those tumor cells. Therefore, you may get the better therapeutic benefits. Okay, these are all basic I want to go through so that you will all have a better imagination or the visualization of your capability, how we can use our nanoparticle for therapeutic application. Okay, again here the various type of nanomaterials, those are in different particle size. Maybe they have a different charge, or maybe if they are not good stable enough, then what, right? So this structure is showing us like how many type of material that you can make and how they fall, right? If you can make like a 1 nanometer particle size, like here. Okay, so I will be changing it to red so that you can. So for example, as I mentioned, you are capable of like make different size range of nanomaterial. For example, if you make 1 nanometer size nanomaterial, okay, what happens that, these nanomaterials are readily cleared by renal mechanism. That means by kidney. Okay, if you take a 1 nanometer particle size, you inject them, they are having a tendency, they will be eliminated by a kidney or kidneys. Okay, if you make a 10 nanometer particle size, okay, those will be readily cleared by liver. Okay, and you see the size range after 10 and up to 200 nanometer, this size range is the best for accumulating nanoparticles at the tumor site by using that EPR mechanism. Okay, so that means whenever you want to make a nanomaterials for drug delivery applications, particularly for cancer therapeutic, you need to make nanoparticle size in this range. That's the number 1 criteria. Number 2 is that zeta potential. Where you see that zeta potential, it could be a positive or it could be a negative based on how you are coating your nanomaterial, or maybe from where from which polymers you are making your nanoparticle, right? Certainly, you should not be making very highly positively charged formulations. If you make highly positively charged formulation, those are very toxic to the all other normal cells. Okay, so you should be considering the particles with the modification. After the modification, particle size, from -5 to +5 somewhere. Okay, not more than that. Okay, if you make any particle size higher than zeta potential +5, those would be very toxic. On the other hand, they can be used for other applications. For example, you want to transfect some of the cells with some of the gene or anything, that case, these particles are better because if you have a highly positive charge particle, they can make a pores on the membrane of the cells and then they can get in. Okay. So, but those are different applications for our drug delivery applications. It should not be very highly positively charged. And also you learn that, once you make the nanomaterial, you have a different coating on the nanomaterial where you are getting the better solubility or dispersibility, right? Here, if you consider about solubility, you have a good solubility, there is no issue. Okay, they can travel into the bloodstream and they can reach to the tumor site. If you have a low solubility, what happens? Those nanomaterials come together and they form an aggregate, and then the particle size will be higher. When the particle size is higher, couple of microns, then you have some type of cells in the body, those are called macrophages. Macrophages, if they know that, there are some of the foreign particles in the body, they can just engulf those cell types, okay? Those macrophages. So they can clearly identify that they will be cleared by this macrophages, they can eat up and, they recognized by phagocysis, they phagocyze all those foreign particles, including nanoparticles. So therefore now, you know that, so now you know that various type of material that you can make with the nanomaterials, and you know that, how many ways that you can improve it. Okay, so this, I think we all learn about this. Yeah, the next question is like, how many different type of FDA approved formulations that are exist for therapeutic application. If you see this slide, I think it's, excuse me, it's a busy slide, but you can appreciate only the use of nanomaterials since 1990, and if you see that one formulation, it's called iron oxide formulation that has been widely used since 1957. Okay, so that means the nanotechnology for medical applications that are exist way before what we are imagining. Okay. The better example I would tell you here, like one drug molecule, it's called, aspirin. You all know that, everyone might have taken one when you feel some of the headache or maybe some type of pain. Okay. So it's this is an anti-inflammatory drug. It can relieve the pain, and also it can be used as a cardiovascular preventive molecule. It has been widely used. So why I want to emphasize here on this molecule is that the same molecule, it has been taken in different forms, and they are modified in different ways that you can improve the same drug activity in the body. Okay, right now the same molecule you can put into the nanoparticles. Here in this case, sodium carbonate based particles. Okay, those will be quickly released into the bloodstream, and they can act much better way, these nanoparticles, when you put this particular drug. Simply, you have not changed any drug, but you have improved the activity of the drug just by choosing a different type of nanomaterial. Well, when we talk about cancer therapeutics, how many FDA approved formulations that are exist, that you can see some of the example, particularly Doxil, and some of that is Abraxane, and a few other drugs are various other types. These are all clinically used for cancer therapeutics application. However, now there are no targeted particle formulations that exist for uh, cancer therapeutic applications. Majority of them are in the clinical trial. Okay, there are formulation FDA approved. Mostly they are following EPR mechanism. Those are still, you modify different things and then you can apply for a chemotherapy application. Whereas, whatever we thought that, targeting only specifically tumor cells, even after reaching to the tumor, those formulations are not very well developed or not approved by FDA. We will talk about the reasons. Okay, but I want to just give you a flavor that different type of nanomaterials, how they have been utilized for various type of drugs. So here platinum drugs like, for example, cisplatin, carboplatin, oxaliplatins, these are the platinum drugs widely used for chemotherapy application, where they kill the tumor cells by DNA binding, and then they cross-linking the DNA. Therefore, it interferes with their DNA repair mechanism. Eventually, that is leading to the cause death of those particular cells. This is a simple mechanism. Why these drugs are preferred means, like, whenever you see in the blood, the less amount of these drug can exist, but you can put, like, in the cytoplasm, they can go more amount of the this drug because of the chlorine levels, chloride ion levels, blood versus cytoplasm. Okay. On the other hand, like, you see this drug is very potent on the cancer cells, but at the same time, it is highly toxic to various other normal cells. Therefore, you see the cardiotoxicity, nephrotoxicity, GI issues, hepatotoxicity, and neurotoxicity, and so on. You name it, there are more than 40 different type of side effects that you can anticipate by using this type of drug molecules. Okay, so then you have the opportunity that you can make different type of nanomaterials and then put this, put this type of drug molecules, and then you can enhance the drug solubility, capabilities of those. The next one is doxorubicin. Doxorubicin, how it works, like basically it intercalate with the DNA, and cleavage of the DNAs is not going to occur, and then therefore DNA breakages can increase. Okay, therefore it prevents the DNA RNA synthesis when you use this doxorubicin or other type of anthracyclines. On the other hand, this drug, again, it's not very selective. It can act majority of this drug on the cardiomyocyte. Cardiomyocytes are exist in the heart, where you see the heart associated issues, including heart attack when you use this doxorubicin. Okay. Therefore, majority of the times, whenever you take this doxorubicin drug to the cancer therapeutic application, the doctor is going to prescribe a pharmacologically modulating agent that reduces the doxorubicin toxicity. Okay, there are a number of pharmaceutical agents that are combined with the doxorubicin is widely used. And the other way, you can formulate the same drug in the nanoparticles, and then they can improve its toxicity on the normal cells and facilitating the drug delivery at the tumor site, where you see the complete elimination of the cardiotoxicity when you formulate into the liposomal formulation. Again, this liposomal formulation further pegylated to enhance its circulation in the blood. Same formulations can also apply for any other drug. Here we are showing you drug called amphotericin B. This molecule is widely used for antifungal activity. Means like the technology would remain same, but you can pick and choose what drug you want to put it in this type of nanomaterial. You can apply for various therapeutic applications. There is another example. It's a drug molecule called paclitaxel. It's widely used for a number of cancer therapeutic application, right from breast cancer, lung cancer, ovarian, and pancreatic cancer. How it works, like it simply stabilizes the microtubulins in the cell. That means you see the diagram. It is showing like beta tubulin formation, how it can be induced by this paclitaxel. Okay, so you see that taxanes, destabilization. If you have a destabilized this beta tubulin, the cancer cells, they grow and then they detach, and then they separate the cells from one to two, right? So they synthesize, and then they go into a mitophagy, and then they separate, right? So that can be blocked by these paclitaxel molecule. Okay, it stabilizes the microtubulin polymerization, and then it never makes separate from one cell to another. Okay, so therefore you have a stopping the mitotic spindling assembly, and therefore you are stopping the cell division. But the problem is this drug is hydrophobic in nature, when you need to improve its solubility. Okay, so you come up with a formulation like a Abraxane, where it is a human serum albumin conjugated with this particular molecule. It can increase the solubility and also inherently targets the tumor cells via some of the protein that is called spark proteins. It's also called GP60 protein. This human serum albumin specifically bind to GP16 receptors, or it can also go through this caveolin mediated targeting onto the cancers. Such way, like you not only improving the solubility, but also increasing its payload at the tumor site. You see the red bars here, how the Taxol, it's a parented like paclitaxel drug molecule have been replaced with the red bars, that is albumin based formulation, that is Abraxane. Okay, so these are the examples, but at the same time you can also increase the sustained delivery of a drug molecule. Here in this case we have a luprolide acetate. It's a prostate cancer drug molecule, like it specifically inhibit the LHRH associated progression of the cells. Okay, where you can put this drug molecule into a PLGA based polymeric matrix. Therefore you may end up having the sustained delivery that can be.
Sir, excuse me, sir.
Yes.
So your slide is present nanomedicine up to date, sir.
Okay, so now. Okay.
Now we leave.
Now it's okay. Okay, so now like with the polymeric matrix that is embedded with the luprolide acetate, it can increase the delivery of the drug for over couple of months. Like for example, based on your PLGA ratio to the drug, you can improve the delivery at the tumor site over a period, for example, 1 month, 3 months, 4 months, and 6 months, depending on the depot that you are making, the composition of this PLGA matrix for this particular construct. There are there are many more examples like that. Another example would be a magnetic nanoparticles, where you can apply for not only for MRI imaging but also for hyperthermia application, not only in the cellular research but also in the human research. It has been proved that hyperthermia indeed helps to the increasing the tumor reduction in the human malignancy, particularly in the brain tumors. So there are many more that we can modify considering the nanotechnology. Here, some of the example. I don't want to go over in detail all those, but just I want to give you some of the example what we do to improve some of these nanomaterials that are already exist and how we take a different approach. Okay, so I listed number of different formulations, but how we want to pick a nano formulation for drug delivery, or how best that you can employ in cancer therapeutics. What we did here, simply we took a natural molecule that's called curcumin, and we formulated with same molecule but with the cyclodextrin assemblies, PLGA nanoparticles, cellulose nanocrystals, dendrometric based nano materials, and then magnetic nanoparticles that are contain these curcumin molecule. So we made all these and then we put it on the prostate cancer cells. Then we identified that you see the structure in the curcumin alone, it shows very few, what you call vacuoles formation in the cell structure because of curcumin. Okay, when you see cyclodextrin curcumin treated cell, there are a little bit more number of vacuole formation. PLGA curcumin base, even you see more number. Cellulose curcumin nanocrystal, you will see greater number, and dendrometric curcumin also you will see greater number of vacuole formation, but all of them are better than your free molecule. Okay, where you see the free molecule only induced only 4 vacuole formation, but all other they produce more than 20 vacuole formation. That means this drug is more potent when you encapsulate in the various type of nanometal. But the last one, you see magnetic formulation of the curcumin, it is completely destroyed that cancer cell. That means it has more potency than any other molecule in these formulations. Okay, therefore we ended up using or focused more on this iron oxide based formulation. Okay, so this is the methodology that we developed, coating different molecules with the iron oxide. Either you use pluronics, you use some of the PhD based formulations, we have a constructing these various type of material, and then we have a patent on this particular formulation where we heavily invested in this formulation to make different drug delivery platforms for various therapeutic applications. Okay, here apart from that, not only for drug delivery, we also can be delivered using that particular magnetic nanoparticles, microRNA delivery or siRNA delivery, or maybe you can use for gene delivery using the same nanomaterial. Okay, so I don't want to go over much cellular work with you all because I'm not sure how much you're all familiar with, but simply this slide is a busy slide. It will tell us right from the synthesis and then its characterization, how much, microRNA exists, how much microRNA is stable when you put into the nanoparticles. And, microRNA is not stable when you inject them. Okay. So they maybe degrade quickly. We assayed all those things using this formulation, improvement of the microRNA stability, and also delivery to the tumor cells, and also activity on the cancer cells. Then we went on and doing majority of the work in the animal models. Okay. Next one is like, so we all talk about PLGA based nanomaterials or nanoparticles, but we want to put some of the targeted ligands that can go and specifically bind to the tumor cells. Again, this is, screening, different formulation and testing on the cell line, seeing its activity, not just by killing the tumor cells, but also seeing, how the pathway it is going in the cells, how biologically it is active, what's the molecular mechanism involved. I know we study all those. Apart from all those, like we want to see whether that specifically bind to the tumor cells or not. You can see this confocal microscopy assay where this all red tiny dots surrounding on the cell, it's specifically binding on the membrane of the cells by using these nanoparticle, indicating that indeed it is very specifically binding on the tumor cells that are positive only for PSMA. But you see on the bottom of the slide, like, labeled with PC3, that is PSMA negative. When you don't have a protein on this cell, you don't have, or you don't see that particles that are going to that particular cell. That indicates that these particles are very specific, that you can deliver drug molecule only to the tumor site. The same thing is confirmed on the mice model, also that having a PSMA positive protein on it. And the next one is like, we all know that, you can simply can develop different nanomaterial, but is there a way that you can deliver more than one drug, right? That's where we thought of developing a formulation that can including more than one drug. And then we have seen that, we put like gemcitabine and gambogic acid, two different drugs that are very active on the lung cancer, where you embed these two drugs, and then we see it's way better therapeutic benefit when we use them combined in a nanoparticle formulation. You see that, here in the gambogic acid combined with it's labeled with GG at, HSA formulation, it obeyed all the, nanometallic characteristics, its activity in the cells. And also once we inject and treated in the mice, we took the tumor tumor tissue and section them and see whether the activity or the tumor growth regression that we are seeing visually is that indeed happening molecular level. We also confirmed by immunohistochemistry analysis. Okay, these are all, the ways that you can see that, activity of these materials in different ways. Well, now, we talk so much about how many ways that, we can treat the tumor cells, right? We were talked about metastasized tumors, right? If it's a one different organ, like, from the breast cancer to it went to the lung metastasis, right? Sometime, you may have a lung cancer as a primary cancer itself, but, some tumors, they go from one organ to the another organ as a metastase. but the common one is, bone metastasis. Okay, bone metastasis you can expect from breast cancer, you can expect from prostate cancer, you can also expect from colon cancer. Okay, so you may end up having a lot more bone associated cancer or bone metastasis cancer. So there is a possibility or bone cancer, like, as a primary cancer also. Okay, so keeping in that mind, you can make a formulation that is also specific to a bone cancer. Okay, this is one of the formulation that we have shown that, our formulation indeed very specific to the bone tumors. Okay, so this way, like, we have a different ways that we can treat the tumor cells. And as I mentioned before, the tumors may contain a different type of cells. Even you can target those cells also. Okay, in some cases, like in the tumor, there are cells called tumor-associated macrophages. Okay, so macrophages in general, those are good. You need to have the macrophages. They can take enough all the foreign materials from the body, right? So that you need to have in the immune system. But when these cells are present at the tumor site, they become as a tumor-associated macrophages. Those are M2 macrophages. Those are M2 macrophages. Those indeed facilitate tumor growth further. That means if you target even these cells, or maybe converting these cells from M2 version to M1 version, it's also beneficial in terms of cancer therapy. Okay, so therefore, like, you can make a formulation that is also be targeting M2 macrophages, can also be beneficial. Therefore, we have made some of the formulation that are targeting to the IM2 macrophages. With this, I stop here. I don't want to take more of your time. I thank all my students, my colleagues over here, and there are a lot more work. We combinedly work with the foundation, some of the NIH and the DOD, and I work heavily with Dr. Chauhan, who presented yesterday on pancreatic cancer, and we work together, more than 18 years in this field, and then we have been doing wonderful in this area. And then if you all have any questions or any other, thing that you all wants to work with us, let us know. We can help you all. And I'll stop here, and then I'll take any questions if you all have.
Sir, participants are no queries, sir.
No questions from the participants?
No questions, sir.
Okay, thank you.
Now it's vote of thanks, sir.
Okay, go ahead.
On behalf of the Humanities and Basic Sciences Department, I, 𝐀𝐝, Assistant Professor in Physics from Gates Institute of Technology, UT, would like to express our sincere gratitude for delivering a thought-provoking knowledge on therapeutic nanomedicine for cancer. Your insightful presentation shed light on the latest advancement in cancer treatment and the potential of nanomedicines in revolutionizing the cancer therapy. We are thankful for the time you took to share your expertise with us and for inspiring our faculty with your passion for research. Your visit has not only enriched our knowledge, but has also opened up new avenue for potential collaborators. Thank you, sir.
Thank you. Thanks, everyone. And you feel free reaching out to me. I have given my email and phone numbers. Or you can reach via email. That would be best. Thank you.
Sir, namaste, sir. Murali, sir. I am Venkata Prasad.
Prasad, etlunna?
Vanan, sir. మీరు వానరా, sir?
20 years అయిపోయింది అనుకుంటా అందరిని చూసి.
2003 సార్, 2005
గుడ్ గుడ్. ఎక్కడ ఇది ఇది
ఢిల్లీ
ఏ
సార్,
ఊర్లో?
ఢిల్లీ.
Oh, good, 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 good. Oh, Delhi. Okay, I visited a year before. I came to University of Punjab.
Oh, okay, sir. Okay. Please let me know, sir. Next visit, we can meet, sir.
Sure, 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 sure. Good, good, good. So
I am in
I
Noida,
want
sir,
to do
actually.
you- Okay,
I am
Noida.
working,
Okay,
I am working in Central Power Research Institute, autonomous body of Ministry of Power.
okay. Wonderful, wonderful. Good to see you.
Thank you, sir.
Good, good, good.
How is children and madam, sir?
No, they're all good. It's early in the morning for us. It's like 5 o'clock.
Okay, sir. Okay, sir.
Right,
Okay, sir.
right.
We'll discuss, sir.
Yeah, yeah, Venkat, yeah, email me, share your number. I'll talk to you personally, okay?
Okay, sir. Okay, sir. Definitely.
Yeah, because we lost the touch, basically with everybody because busy in their own way.
Sure, sir.
Okay,
Sure.
share your number. We'll talk more. Okay.
Okay, sir. Okay, sir.
Okay. Wonderful.
I will take your number, sir, and I will share it.
Yeah. Yes.
I will talk. I will take your number from Swami and I will share it.
No, I think you have in the WhatsApp group, right? That Scupa.
Yes, sir. Yes. Scupa,
Yeah.
I'm not there, sir.
You're not there, okay. But yeah, that's okay. Okay.
Okay, sir. Please
Okay.
let me know, sir. I will inform.
Okay. Good.
Okay, thanks.
Thanks,
Thank you, sir.
everyone. Okay.
Okay,
Bye.
sir. Okay, definitely.
So before online test, good evening one and all. So dear participant, as we come to the end of all the remarkable session by our eminent keynote speakers who have shared their experience and knowledge on various topics related to recent advance in novel drug delivery application. There will be an online test to showcase your understanding levels. The test will be activated for 1 hour exactly from 6:30 p.m. to 7:30 p.m. So all the participants should make use of it visually and complete the test within the stipulated time through the Atal FDP portal. It is mandatory for certificate approval. All the best participants. Now, validatory for this FDP. For this session, hand over to Dr. Rizwan sir.
Once again, good evening, one and all. I welcome to you all the validatory function of your FDP, our novel drug delivery applications. That was a resounding success. I take the opportunity to acknowledge the efforts and dedication of all participants who have successfully completed the FDP. Our commitment to enhancing our teaching and research skills is a truly commendable. This FDP was designed to enhance bioavailability, targeted delivery, minimize of targeted effects, and enhance therapeutic outcomes. We have had a privilege of learning from renowned experts in the field and engaging in meaningful discussions. I extended my sincere thanks to our Managing Director, Correspondent Director, and Principal for their encouragement and guidance for this FDP. I would like to express my sincere gratitude to Atal FDP team and Mr. Imtiaz AO for the constant support throughout the FDP. Dr. G. Haripriya, convener, smooth functioning of the FDP program. Dr. D. Jhansi Rani, coordinator for the FDP program, is incredible support to the FDP program. Mr. 𝐾𝐲𝐶 sir for the technical support for the throughout the program. Mrs. I. Suman, content writer, thanks to Suman Madam. Miss Puspa and Miss Maunika for player designs and constant support to our FDP program. Mr. S. Nasir for the press note, who are felicitate and support for their outstanding contribution in making this FDP a grand success. In conclusion, would like to thank everyone once again their participation and support. We hope that knowledge and skills you have acquired during this FDP will benefit you in your academic and professional experiences. Let us look forward to future collaboration and endeavors. A big thank to one and all. All the best for the online FDP exam. That exam is more important to get the certificate.
Sir, again, no need to attend 7:30. Shall I close the session, sir?
Close, sir. So every
Hello, sir.
participants should go to that Atal FDP portal and do that your login details, enter that. Then after that,
Hello.
write the
Hello, sir.
test.
Hello. Hello.
Sir, tell me, sir.
Sir, can I speak? I'm one of the participants.
Tell me, sir.
Sir, I would like to thank the organizers of your entire college to conduct this nice Atal FDP, sir.
Okay, thank you, sir.
And we learned many new things, sir. And one small request, sir.
Okay, sir.
Sir, now I just tried to log into the Atal portal. Its server was a little bit down, sir. After 3 times, I could able to log in. So I request you to kindly extend the time if possible beyond 7:30 because of this server issue.
So sorry, sir. That is related to that portal, sir. So
Yes,
we give that only they are give the time only time, sir. We give the only 1 hour or 45 minutes they given. I will like that 1 hour. I give that time, sir.
3 times I could able to log in, sir. But if in between any problem comes, there is no alternative for us now.
That's why we give that only 20 bits we have to give, sir.
Yes,
in
sir.
online
Yes.
portal. So with 1 hour we have to give the time.
Okay, sir. Okay, sir. Thank you, sir. Thank you.
Okay, sir. So any queries, participants? So thank you for your participants, sir.
Good evening, sir. This is Dr. Sidra, one of the participants. Am I audible, sir?
Good evening, madam. Audible, madam.
Sir, I have submitted all the feedbacks and I have attended all the sessions of FDP, but it shows that one particular day is absent in Atal portal. Kindly rectify that. And I thank you for the organizing team for your wonderful workshop, wonderful FDP.
Okay,
Thank
madam.
you so much, sir.
Thank you, madam. We will rectify the attendance, madam. So we will do that. So first we need to concentration on that test, madam. Without writing that exam, we are not helpful us to the certifications, madam. So
Okay,
please,
sir.
every
I'll take the
participant
test.
needs the certification. So we write that exam. After that, we have to get the certification.
Okay, sir. I'll take the test, but it is showing that there is no feedback regarding this particular FDP.
So
I need clarification regarding this.
we will change, madam, all the participants. So don't worry for the attendance. We will give the attendance, no problem. So we will rectify by tomorrow. So what
Okay,
the
sir.
attendance, we have to take that feedback online.
Okay, sir.
Okay. So
Okay, sir. And what about the feedback, sir? Attendance is okay, feedback?
Feedback is online through Atal portal only. We have to fill that feedback, madam.
Sir, they send the
that is regular
link.
feedback, madam. So oral
Okay.
FDP feedback is available in Atal portal.
Okay, there is no issues regarding this, right, sir?
No issues, madam. This is our availability purpose. We have to take that PDP.
Okay, sir. Thank you.
Excuse me, sir.
Sir, what about today attendance, sir? Is there any link sent?
No link, sir. Directly you have to fill that. You write the test, sir.
Sir, for test, which link we have to click after login?
What, madam?
After login in the Atal portal, which link we have to click for writing the test?
Test and the preview is there, madam.
Preview.
You will go for Online test, madam. Test is there, na?
No, only marks are there. No test is there.
Shall I answer the for
Assessment
this
we have to-
test?
Madam, left side there are two lines are there, madam. So you keep click here, click there. So there are some line number of words, the attendance and particular things are given. Feedback, attendance, test, they are given. So the test marks we have to write. The test we click, we write that exam, madam.
But sir, here test is not given. Only
No, madam.
Madam, 6:30 will enable, madam.
Okay.
On left side,
The assessment is there.
assessment tab is there, madam. You can click on the assessment tab. You will find
Okay.
the FDP which you attended. So where you can find the link. By clicking the link, you can agree the terms and conditions so that then the test will start by 6:30 p.m.
Okay. So by 6:30 only we will be able to get the link.
Yeah, because I tried just now, but it is showing that you have to start the exam by 6:30 only.
Okay.
Just go to the assessment tab on left side.
Okay. Yes, I have gone.
Where you will find all the FDPs which you attended by the registered mail ID. So in
yes.
that
Yes.
you click the FDP, you click the present FDP, so
Yes.
that the link will present over there, and you can click the link to attend the exam.
And we have to click the start button, right?
Yes, and every question you have to answer and save, and you have to move to the next question. That is the procedure, basic procedure of Atal FDP exam.
Okay. Done. Thank you, sir. Thank you.
The assessment link only available 1 hour. That is 6:30 to 7:30. After that, that link will be disabled. Please. All the participants should write the exam.
Okay, sir. Thank you, sir.
Participants, any queries? Yeah, that assessment link will enabled 6:30 to 7:30 only. After that, that link will disable. Please be careful.
Go to the assessment tab.
Sir, any doubts regarding the Atal FDP exam assessment?
Fine.
Yeah. Sir, don't worry about the attendance. I will resolve that problem by tomorrow. Okay. Please concentration on the online test and feedback, Atal online feedback. All the participants was gave to every day Google form feedback. That is not considered. Atal, you go through Atal FDP feedbacks, then fill the ratings 4, 5, 6, like that, then submitted. That is considerable in Atal FDP programs. Any doubts? Assessment is the most important. Feedback, all the participants first fill the feedback, then only your assessment will be enabled. First fill the feedback. Only 20 bits are there. Only that time will take only 20 minutes. You have plenty of time in your hands. That is a 1 hour. No problem. Don't hurry up and don't bother. Don't worry about the exam. Receive the phone. Madam, all the participants should be given feedbacks and online test in only Atal FDP portal only. The left side corner having the feedbacks, assessment and test marks in your participation login. Go through and then first fill the feedback form, then write the exam. The feedback will time only within 5 minutes. 5 minutes enough to fill the
Hello, sir. Good evening, sir. Hello. Hello, sir.
Sir, tell me, what is your problem?
Sir, good evening, sir. Myself, Shanmugan, sir. The assessment link with open, sir. After next Tuesday,
sir.
Assessment link with open, sir.
But that is enabled 6:30 now. 6:30 now.
6:30 now. 6:30 now.
Yeah.
Okay, sir.
6:30.
Okay, sir.
Please Google it. Okay.